I'm back to my YouTube channel once more. Today was still Power Machine M6. This is an internal combustion engine. So let us look at this typical question. So it says this question: in a trial of a you can see 6-cylinder, 4-stroke, right? It's not a 2, it's 4-stroke engine. A Morse test. This is a Morse test. We're under the Morse test. All right. Was carried out when full running at the load and all cylinders. Check all the cylinders working. The brake power was for all. For the all, they were sharing this brake power. They were sharing that brake power. Then they say the measured brake power when each cylinder was cut out in 10 and load reduced to bring the engine back to its original speed as follow. We've given cylinder 1, cylinder 2, cylinder 3 until cylinder 6, and then we've given each brake power in kilowatts. So we've given for cylinder 1 brake power, for cylinder 2 brake power, for cylinder 3 brake power, for cylinder 4, so and on and on. So since you've given that, we want, remember, initially they are running at this, at that they were running at this for the whole, all they're sharing that initially. So you'll get it there on the question, will be given there on your question, the initial one for the whole. So all right, so if given 4.1 says calculate what mechanical efficiency. All right, we want mechanical efficiency, right? We know that mechanical efficiency must be given by which is brake power divided by indicate power multiplied by 100, right? So that is where we'll get the mechanical efficiency here. So let us try and calculate what the indicated power. Let us find the indicated power. How can you go about getting that, the indicated power? Then the brake power we do have. The brake power we do have. All right. We took header. So how can we go about determining this typical indicated power? All right, so you're supposed to know that this will be indicated power. You're supposed to know that you just will focus on the first cylinder first, and then we go on and on. So the indicated power, I can say the indicated power 1. All right, the indicated power 1 must be equals to what? To the brake power for this whole, must become the brake power for the whole initially, for this whole engine. Remember, this is an engine, just has 6 cylinders. For this whole engine will be 56. The total of your 16 kilowatts minus this one that we are given for what? One, the indicated power, where on the first cylinder. To calculate the indicated power is simply what? The brake power for the whole cylinder minus the one that we are looking for, which is 44.2, right? So what are we going to have as the indicated power? There you subtract, you'll obtain 12.1 of your 16 kilowatts. All right, so let us get again indicated power 2 for cylinder 2. We will still have 56 minus now the brake power there at that cylinder, which is 44. This will give us what we will going to obtain 11,7 kilowatts. So indicated power for cylinder 3 we still have 56 minus the brake power at that cylinder. All right, this will give us what 11,9 kilowatts. So again, the indicated power, we still have the indicated power at cylinder 4 will have 56 minus that 44,3. What are we going to obtain there? What are we going to obtain? 12,3 kilowatts. Then indicated power for cylinder 5 there, fifth cylinder will have 56. Subtract the indicated power at that portion, at that cylinder. We must obtain that we have to obtain let's try and let me try and check for one. Let me try 56 minus this for the first one. All right, for the first one, okay, let me say think here. All right, I've punched wrong values, sorry about that. For 56 minus 42, that I think you'll obtain 11,8 kilowatts. Then 56 minus 44, you'll obtain here 12, obviously, kilowatts. For this guy then you'll obtain what then? Obviously you'll obtain 12,1 kilowatts, isn't it? We together, so 56 minus 43,9. all right, so what about this one? 56 minus 44,3, right? You'll have 11,7 kilowatts. Then the fifth one will have 11,9 kilowatts. All right, all these must be in kilowatts. Then let's check the last one, the indicated power for cylinder. What is that? Sixth cylinder will be 56 minus 4,37. right? What will be the value that will obtain? 12,3 kilowatts. all right, this must be in kilowatts. So this is how you determine this. Now after we have determined this, let us add all of these values. Let us add all of them. You add, simply just add, right? When you add, you'll get that the indicated power, the total one, supposed to get the one that we'll use. You add 11,8 plus 12 plus 12,1 plus 11,7 plus 11,9 plus 12,13. You're supposed to get 71,81. 8. Will be 8, right, kilowatts. So this is what we'll use. This is our indicated power that we'll use on the problem that we'll use there. So we have seen that the efficiency will be equals to brick power divided by indicated power multiplied by 100. So we have the brick power, obviously is 56, is the one that we have. We have the original one for the whole cylinders, this is 56, right? Because we'll have 56 divided by this one, the one that we had, 71 indicate power divided by 8 times 100. This will give us the efficient term. We will have 77,99. Obviously it's in what? It's in percentage. Percent. This is what you have there. That is what you'll obtain. Are we together? So 4.2, the mass of fuel used in kg. Check in kg per watt per minute. There they want us to find the mass of fuel, per minute, per min here, per min. So how you'll obtain that per min? So we'll have ISFC multiplied by indicated power divided by 60, because this is what it is, 60. It is 60 fuel per. Remember, fuel there on the top will correspond with that fuel. Remember, this AIS is this guy that we have given. It's an indicated specific fuel consumption, this one. All right, whereby we given it to be 0.6 is given in kg, like this actual kilowatts per hour is given in that, which is 0.6 there, 0.26. We took care of given that with 0.26. So let me just write here 4.2, the mass of fuel per minutes. We'll have multiplied by indicated power divided by 60. Are we together? So let's go, let us substitute, determine this. We've given to be 0.26 multiplied the indicated power. Obviously is the one that we calculated, the one that we used there, which is 71.8. So multiply by 71.8 divided by 60. So what will be our fuel per minute? All right, so we'll obtain fuels per minute. So we'll obtain 0.311 kgs. Obvious fuel is measured in kg, but what be per minute? This will be per minute. So that is it. So let's check 4.3. What do they want? 4.3 says determine the mass of the exhaust gas in kg per minute. The mass of the exhaust gas. The mass of the exhaust gas in kg per minute. Take note there. You want the mass of the exhaust gas per minute. You want this to be per minute. It is in it. Must be in per minute. All right, how can you go about that? So we'll have, this will be what must be the mass of the fuel, but we know that the fuel, our fuel was what was in per minute there, as you can see. So that will be is what will obtain. Multiply this must be multiplied by the, we've given fuel ratio. If you can check what they're given here, indicated consumption, what we're given here, and then heat value, air fuel ratio. Check, we've given air fuel ratio, which is that is 5 comma, and then we have 1 there, fuel ratio. So if you have given ratio, we've given fuel ratio, I just multiply by fuel ratio. Fuel ratio, I'll just say fuel. I will write like this: AF means fuel ratio. Fuel ratio. Obviously, remember it is 15,2, but remember into what 1. So fuel, this is air fuel, right? It's air. Remember that thing is mixture. We mix with this. If you've given fuel ratio, you add this one here. You add this one, be 15,2 plus 1 plus this one that you have given, that ratio there. You add that one. But anyway, it's a fuel ratio, isn't it? Plus 1. We took it. So we'll have this guy we've calculated there will be 0,311 multiplied by then fuel ratio there, which is, I've just talked about this fuel ratio you've seen here. Fuel ratio, it is 15,2 into 1. So you put that 15,2 plus that one there. So punching this will obtain this in this exhaust, the mass of exhaust per kg per minute. So kg per minute, we'll have our 5,038 kg per minute. So this is what we have obtained so far. All right, so we have to keep on tracking. 4.5 says determine 4.4 the heat loss to the exhaust gas in kilojoules per minute. The heat loss, the heat is an energy. The heat lost by what? By the exhaust, not just the heat. The heat loss of what? Of the exhaust. Heat loss of what? Exhaust. Right. The exhaust gases. Obviously, the heat will be the mass of the what? Exhaust gases. Mass of the exhaust gases multiplied by what? By specific capacity multiplied by what? By change in temperature. You know this formula, most. That is what is the formula that we use. Obviously, it's a formula for what? For heat. But the mass here will be the mass of the exhaust. Well, luckily here we've determined the mass of the exhaust by is this one, which is 5,038 multiplied by specific capacity. So what is the specific capacity? Are we given the specific heat capacity of the exhaust gas? Take note there. So do not use this one is for the heat of the exhaust gas is 1.1. So we've given the 1.1 multiplied by the change in temperature, which is, we know change in temperature is T2 minus T1. We took care of T2 minus T1. Let's check the final temperature. There we've given the exhaust temperature, the 400 gas, right? Subtract the initial one, the normal air temperature. Obviously, the exhaust, you use the exhaust gas minus the normal, the first one, the normal one. So must know that the change in temperature will be the exhaust one temperature minus the normal temperature. So that is what we'll have there. So we've seen that the exhaust was 400, the normal one is 18, if I'm not mistaken. Yeah, it was 18. So what we'll obtain here. Plug punch that. You'll have something like 216 116 comma 97. Obviously said they want this in what? This obvious will be in kilojoules per minute. It's because why this guy, it's in minutes, it's in kg per minute. We'll get it here. Right, so this is what we'll have there. So we'll have now 5.4.5 4.5. We're supposed to have 4.5. All right, what is going on? Oh, okay, we are done with 4.5. Is 4 point not ish. Let me write 4.5. I'm writing 4.4 here, 4.5. So I think 4.5 says the heat loss to cooling water, kilojoules per minute. You see, cooling water, talking about water. So the heat of what? Of the water. W, the water. So we use the same formula, specific change in T, but now will be what? The mass of what? Of the water, specific capacity of the water, multiplied by change in temperature, isn't it, related to water. So let's check now. We have, what is this mass there? So the mass of the water, the mass of the cooling water, flow rate for check is 43 kg, which is fine. That kg means the mass per minute is right. We're for the 34. And what is the specific capacity of the water? You see, specific capacity of the water is there, 4,187. All right, 34. There we've seen multiplied by specific. It was 3, it was 4,187 multiplied by this change in temperature. Let's check now the change in temperature. What will be that? Can we have our change in temperature? Let me erase a little bit here. So the indicator, we have that the heat, the exhaust gas temperature, given specific heat capacity, the cooling water temperature rise, that means already this is a change. You see, the cooling water temperature rise. This is a change already. The change is 38. That means there we have our change. There will multiply by what? Power 8. That will be the change. Then this will give us what? The heat there will be 5409,6 kilojoules per minute. All right, kilojoules per minute. That is what we have now there. So let's check 4.5. What cookie crumbles there. So it says draw up a heat balance in you see in kilojoules per watt per minute as the percentage to determine percentage loss of the radiation. Assume that the heat loss to friction is absorbed by the cooling water. All right, so let us formulate the table. I like to formulate some table. Formulate some table. All right, formulate the table there. um all right, so we'll have heat gain here. Start by heat gain, heat gain, heat gained, heat gained, obviously heat gained in kilojoules per minute. If here they said to show that, what will be the heat gained? There we'll have heat gained, right? Here we must what must have heat supply. They must have the heat supplied. Obvious also must be in kilojoules per min. This is our balancing sheet we took at. So let's see how the cookie crumbles. So let's find the heat. The total heat will be the total heat. You always will have this heat will be the mass of the fuel multiplied by caloric value. So this will be equals to what? 0,311. We've seen the mass of the fuel, we've calculated it, multiplied by what is caloric value. The mass of the fuel is this one here. We did determine correspond with that here. That is why I'm using it here. So what about the caloric value? Caloric value, let's check the heat value. It's the same as like here. The heat value is 42 megajoules. Remember, we must use this in kilojoules, not in megajoules. So 42 times 10 to the power of times 1000. You must use this. Must be, we have given 42 megajoules. Must be in kilojoule. We have 42. Must be in kilojoules times 10 to the power of 3. Now it will be in kilo. So that is what we'll have there. All right. So times 10 times what there? Times 42 times 10. 42 times, yes, 42 times 10 to the power of 3. This will be what? Will be 13062. Obviously, since we have written the SI units here, there is no need to write it there on the blocks. All right, we took care there. So let us have our thing now. We did have the heat supplied. All right, we did have some heat supplied. So let us try and have now our things. So I will draw. Let me start by this. Draw some columns like this. So in this line, in this first row, I will have the, let me say here, I forgot percentage here. Let me write percentage obviously there. Heat supplied, then we can have our percentage in that column. Let's have the percentage. All right, percent, I forgot the percentage. I wrote my percentage. Right, we have the percentages there. So this is our table. Let's go. We'll start by the brick power. What we have there now, we have brick power to get brick power, the heat for brick power. We have brick power. Brick power, obviously, you have given this will be 56 multiply. Remember, must be heat for brick power. The heat for due to brick power must be in kg per minute. So this is must multiply this by what? By 60. So this will be what? There will be 3360. All right. Then the heat of water. Then the heat of water, I think we don't have to do nothing. It's already in kilojoules per minute. Check the heat of water. It's already not in kilojoules per minute. You simply just take this as it is. There's no need to do anything there. All right. So let us take it as it is. There it's 5409,6. Obviously it's already not in kilojoules. That is the heat. It was the heat, obviously. Now again, let's check the heat of what? Of the exhaust. Here we did the exhaust. Guess what will be the heat? Let's check. We did calculate the heat and then it was in kilojoules per minute already. So is this 2116,97, 2116,97. Obvious already was in what? In kilojoules per minute. All right. So there is this what we call unaccounted. The one that unaccounted, they will have what we call unaccounted like this. What will be the unaccounted heat? So let me just write it here below or above. Unaccounted heat. I want you to check the unaccounted one. Unaccounted heat. Unaccounted will simply be what? Unaccounted, you must take the total heat. This heat there, the total heat, the one here, which is 13062 minus this whole heats that we've just determined, minus this, minus that, minus that. So we'll get to, so you have 3360 minus 5409,6 minus 2116,97. So what is that are we going to obtain? There will be 2175,43. all right, this, remember it was what? Kilojoules per min. So because all of this is given in kilojoules per min, so this is what you're supposed to put there, 21,75,43, isn't it? So how do we go about determining the percentage? Determining the percentage, you take the total heat, the total, this one, the total, let me just, because we are done with this here already, here you've shown, let me erase here and add something here. We're supposed to have what we call now total here. We're supposed to have what we call total. We'll have this row will be for the total. We'll have our total here, heat, that one, the total heat. You add all of these heats, 1 2 3 4, and see what you'll obtain. obviously must be equals to this, will be 13062. That is our total heat there. All right, we know that it's in kilojoules per minute. So what about the percentage for each percentage for brick power? So we must take the brick power, will be the brick power 3360, divide by the total heat is 13. Here is 13062. Multiply this by 100. So you'll obtain the answer. So and on, what will obtain there is 25,72. There is no need to write percentage. Already I've shown the SI units there. The percentage 25,72. You come again to this. For water, you will take the water 500 and like this 9,6 divided by the total heat 13062. Multiply this by 100. You'll obtain this to be 41,41. Obvious will be the percentage, because here it's in percentage. This will be in percentage. That is what we'll obtain there, isn't it? So you are done with that. Let us go to the exhaust. We'll have 2116,97 divided by 13062 times 100. This will be equals to what? 16,21. Obviously percent. Let's go to unaccounted. 2175,43 divided by the total heat 13062 multiplied by 100. This will be what? Will be 16,65. The total percent must give you 100 if you add this. If I'm adding 25, that, adding this percentage, I must obtain 100. So this will be our total, must be 100%. Obviously, this is 100%. So this is how you balance the heat, but this is how you do the heat balance. So thank you for watching, guys. If you found my video helpful, do not forget to subscribe and click the notification button so that you'll be notified whenever I post a new video. All the best.